All right, today we're going to talk about what we call volumes of revolution. This is the other way to find the volume of an object besides using cross sections. So this is volumes of revolution part 1. The part 2 video will be the one on Thursday. Okay. So when I say volume of revolution, what I mean is taking a shape like a rectangle, and I'm going to revolve it around an axis, say the x-axis. Let's turn it this way. If I take this thing and I revolve it around the axis to where it makes a solid, what shape will the solid be? It'll be a cylinder, right? Now, am I actually making a cylinder? No, but can you visualize what I'm talking about? Okay. What shape is the base of that cylinder? It's a circle. Agreed? All right. What about, say, a triangle? What if I took a triangle and revolved it around the y-axis? What does that make? It makes a cone. What shape is the base of a cone? So no matter what shape you revolve, if I revolve some weird squiggly shape, isn't the base of it going to be pretty much always a circle? Yes. Okay. So that is how they find the volume of unusual shapes. They take it, they revolve it around an axis, whatever the shape of the outline of it is, and then talk about it that way as an accumulation of a bunch of circles. So let's start with this example. We are going to revolve y equals sine of x from 0 to pi around the x-axis. They will always tell you what to revolve around. Today we're going to focus only on the x and the y-axis, on revolving around other lines besides the x and y-axis. Okay? So, first thing we're going to do is we're going to draw basically a cross-section of what this is going to be. So, I'm going to draw an axis, take my calculator, type in sine of x, and I'm going to use the interval that they gave me. So in this case, I want to go from 0 to pi with a scale of 1. Looks good. Now, think about the sine wave. How high and low does the sine wave go? -1 to 1. So we want to go a little bit higher. Let's say -2 to 2. So 0 to pi for x, -2 to 2 for y. Go ahead and put graph when you're done. So, wow, very simple shape, just a hill, right? So, I'm going to draw it a little bit steeper here because I've stretched it out a little bit. Right there. There's my shape. 0 to pi. And I'm going to lightly shade it in because you have to know what the original piece is. Now I've already got a cutout of this right there. Mine's a little bit steeper. So if I take this and revolve it around the x-axis, what's it going to look like? Is it a sphere? It's not a sphere. It's not a circle either. It's okay. An ellipse is flat. Okay, it's what we call an ellipsoid. What's a real world something? What's it going to look like? Say it again. An egg or a football. It's usually the guys who say footballs and the girls who say eggs. Okay, so to go along with it, since it's Easter, there's an egg. Okay, isn't that what it's going to look like? Yeah. Okay, so that's what you're going to have. It's almost the same size too, isn't it? Okay, which I think is kind of cool. All right, so what I need you to draw is every time you do this, whatever axis you're revolving around, I need you to draw the mirror image of it with a dotted line on the other side of the axis. So it's basically now like you're looking like at a cross section. So that is a cross section of that egg. You agree with me? Okay. Now, if I had a laser, okay, and I could take this egg and I could slice it through the axis of revolution, teeny tiny thin slices. What shape, if I'm going this way, would the slices be? They would all be circles. Do you agree with that? Okay. Would they all be the same size? No. At this end, they would be microscopic. In the middle, they'd be a lot bigger. They would be basically the diameter at that point. Agreed? Okay. So, what I need you to do is to draw in slices right here. I draw a little bit of a curve, and then I draw one right next to it. Now, because those slices actually do have a little bit of thickness, I draw 2 lines instead of 1. And then kind of go like this. Do you see how I did that? So that's one of those slices. Now, this has a lot of correlation to the cross-sections worksheet that we did because you're looking at the area of a slice. Okay? The slice is what we call a disc. We don't call it a circle, we call it a disc because it actually does have a little bit of thickness to it. Like a CD. What does CD stand for? Compact disc. It's a disc because it has some thickness to it. That's why they call it a disc. Okay? You need the formula for the area of that disc, which in this case is what? Pi r squared. Now, here's the question of the day. What is the radius? The radius is always measured from the axis of revolution into the original piece. So when you draw your radius, you have to draw it into the original piece. It would be, is it X or Y in this case? It is Y. It can't be a number like 1 or 2 because it changes as you move across the egg. But it's always going to be the Y value of the curve no matter where you slice it. Does that make sense to everybody? Okay? So, when we set up our integral, whatever axis you revolve around determines whether it's dx or dy. If you revolve around the x-axis, it's dx. If you revolve around the y-axis, it's dy. Last class, it was whichever one is perpendicular to. This one is the one you revolve around. Okay? And because that egg is comprised of all of those slices put together, added up, we integrate, because integrate adds up the whole amount. And it is the area of one slice, just like we did with the cross-section, so it's pi y squared dx. Now, because it's dx, what do you think the limits of integration would be? Where do the slices start and where do they stop? 0 to pi. Okay? So 0 to pi says I'm adding up all the slices starting at 0, going to pi of each of the circles with a thickness of dx. That's what it's saying. So now we do it like last time. Pull the pi out. 0 to pi. I need to change the y to an x because it's a dx problem. What should I use? Y equals sine of x. It's right there. So this is sine of x, the quantity squared, dx. And that's what goes in the calculator. So, pi first, and math 9, 0 to pi. Got to put another parentheses in there. Sine x, close twice squared, dx. And you get 4.935 units cubed. Any questions? Yes, ma'am. Okay. Good question. All right. How do you find the volume of a cylinder? Don't you take the area of the base times the height? This is the area of the base, and the height is from 0 to pi because it doesn't change. Because it changes, you can't use just a number. You have to say from 0 to pi. Yeah. Exactly. It's a good question. It's a very good question. Any more questions? Okay. Next problem. This is the pen I don't like. Move over. Y equals 2 plus x cosine of x from negative 2 to 2 around the x-axis. 2 plus x cosine of x from negative 2 to 2 around the x-axis. So, since I'm going from negative 2 to 2, I'm going to need both quadrants. So I'm going to move this over just a little bit. Clear that out. 2 plus x cosine of x, window, negative 2 to 2. That's easy. Now the height. Now I did this last period, so I know what I need to make it. Negative 2 to 2 doesn't work. It cuts a little bit of it off. So we're going to go negative 4 to 4 for the y's. So negative 2 to 2 for the x's, negative 4 to 4 for the y's. And then push graph. And that's kind of a fun curve. I like that curve. Now, can you draw in the mirror image of that over the x-axis? Draw it dotted. Draw it dotted. Like that. Yeah. That's what I see too. Draw a line straight down at each end. Like so. Shade in the original piece. Don't shade the whole thing, just the original piece. It's very important. It doesn't make as big deal today. It does big time on Thursday. Okay. Sibby says she sees a fish. Does anybody else see another shape besides a fish?
A whale.
If I take this thing and rotate it this way, I see a vase too. Okay. Yes, that was mentioned last period. Turn it this way. It looks like a mannequin head that's kind of been flattened on top. The head and the neck. Another one that somebody mentioned last period this way is a bowling pin. The top of a bowling pin. Just round that off down on the sides. Make a bowling pin out of it. No, at the top it's just rounded here and then it comes down big at the bottom. Yeah. So, I like the bowling pin or the mannequin head a little bit better than a vase because vases are hollow. This is not hollow. This is solid. Okay? I can see that as kind of an unusual looking doorknob too. Can you see the doorknob? Like this? I just saw that. The what? Oh, the little horn. The horn on a bike. Okay. Now, draw your slice in. Shh. When you draw your slice, you've got to remember it has to go from the edge of the original piece to the edge of the mirror image. Okay? Okay. Now, because the piece touches the x-axis all the way across, it's definitely going to be solid. We're going to have some in a minute that are not solid in the middle, but this one is because it touches the axis of revolution. So that's considered a solid. So the slice is still a disk. The area is still pi r squared. Is the radius still y? What do you think? Is the radius still y? It always goes from the axis of revolution to the original piece. And in this case, that is in a vertical direction, so it is y. It is still y. But it's going to be a different y value that we plug in. So now, we write our integral. Is it dx or dy? Dx. And it's still going to be pi y squared, just like before. But the limits of integration are different this time. What are they? Negative 2 to positive 2. So we can pull out the pi, negative 2 to 2, and y this time is equal to 2 plus x cosine of x, the quantity squared dx. Now, when you type this in the calculator, you've got to put a second set of parentheses around the whole thing, or it's not going to work right. So when you plug this in, bless you, we have pi, math 9, negative 2 to 2. Another parentheses, 2 plus x cosine of x, close twice squared, dx. Yes?
Is there, like, limits that they give you in the problem if they're bracketed in, like, numbers? Are they always going to be your numbers? Like your
90% of the time, yes. I can't guarantee it every time. Because if it's revolved around a different axis, they're going to change. So 52, are you getting 52.429? Is this pretty easy? Is this pretty easy so far? Okay. Now we need to move to where we revolve around the y-axis. Not that much different. This pen doesn't write as well as this one. Y equals 4 minus x, comma, x equals 0, comma, y equals 0, comma, around the y-axis. They did not give us a domain this time. So we're going to have to find it out. Since we're revolving around the y, we're going to need both sides of the y-axis. Now, you should be able to figure this out without a calculator. 4 minus x, what kind of graph is that?
Linear.
It's linear. What's its y-intercept? 4. So it's up here. Slope is negative. -1, so it's going to go like that. And because it says x equals 0 and y equals 0, that means the x-axis and the y-axis. So basically, we're talking that triangle right there. I'll shade that in. We're dealing with, not that one, this one. That triangle right there. We're revolving it around the y, so it's going to look like a cone. We've already talked about the cone. So draw the mirror image on the other side. And then draw your slice. Make sure it goes from piece to mirror. So it's going to go this way. There's my slice. Is a cone solid in the center? Yeah, in this case it's going to be. The piece and the mirror are solid, okay? So, the slice, once again, is a disk. The area is still pi r squared, but the radius is not y anymore. Because the radius goes horizontally this time, the radius is now x. Does that make sense to everybody? Okay. So now, because we go around the y-axis, it's going to be a dy, and it's going to be pi x squared. My limits have to be y values. The bottom of the cone is where? 0. The top of the cone is 4, because that's the y-intercept. So from 0 to 4. All right, so pull the pi out. 0 to 4. How am I going to change x to y? Right here. So y equals 4 minus x. So x equals 4 minus y. So it's 4 minus y, the quantity squared, dy. When you type that in the calculator, you can type it in as y's or you can type it in as x's, and you'll get the same answer. Now I'm going to do something a little different this time. I'm not going to put the pi in the calculator, and I want to show you something. Let's see here. Math 9, 0 to 4, parentheses, 4 minus y for x. I'm going to do it with x squared dx. And I get a nice, honestly, a nice pretty answer, 64 thirds. So this is really 64 pi over 3. All right? Now I want to show you something. Because it's a cone, We can find its volume with geometry, can't we? Now, on the AP exam, they want you to use calculus, and I don't think they'd ever even give you one that you could do with geometry. Who knows the formula for the volume of a cone? Not 4/3. 1/3 pi r squared, the area of the base, times the height. Okay? So it's 1/3 pi. Now the r, in this case, is the radius of the base. What is the base of that cone? What's its radius going to be? It's going to come out exactly 4 units on that side. So it's 4 squared. How tall is the cone? 4 also. 4 squared is what? Times 4. 64. 64 pi over 3. Same answer. Pretty cool stuff. And calculus is probably how they...
doing that way?
No. You would have to do it, yeah. There was a big mess about 10 years ago where they wrote a problem in the AP exam that the physics students had an advantage on. And you could do it with physics and you could do it with calculus. And some of the physics students did it with physics and they got it wrong because they didn't use calculus. It's not fair to use a subject that you're not being tested on. You could use it to check it, but you couldn't do the original problem that way.
Then you get points for your work and your answer, not just your
Well, I don't think they gave him any points. Well, I don't know if they did or not.
Graded based off your work and your answer.
All right. We have one more problem we have to do. So let's move on to the last one. We're doing great on time today. The last example. A little more complicated because we use multiple curves. This one is y equals cosine of x, y equals sine of x, and the y-axis. Sometimes they'll just say y-axis instead of x equals 0. We're going to go around the x-axis. So this one looks a little better if you draw it a little bit bigger. So I'm going to draw kind of a big graph this time. So cosine of x and sine of x. And the y-axis, which we can just look at. So let's just do a zoom 7. Because that's the trig window. Let's see what that does. Here comes cosine. High, mid, low, mid, high. Here comes sine. Mid, high, mid, low, mid. What are we talking about? What's the piece that we're talking about? It is kind of a double helix. It is. But if I'm only looking at the piece that is bounded by cosine, sine, and the x-axis, it is the tiny triangle right in there. Exactly. Do you see it? It has to be the cosine curve, the sine curve, and the x-axis are the 3 sides. Do you see the tiny triangle?
Yes.
I'd zoom it in if I could, but it won't let me. So we're talking about that little triangle right in there.
Can't zoom it in.
Not while I'm recording.
Well, then you can zoom in on
I can
better.
zoom in like that.
So where's which one is it?
It is, let me
Right.
put my fingers right here.
Y-axis.
That triangle right there. Above my fingers. Okay? You see the little triangle? Sorry, I'm moving. Okay. So we have to draw this piece coming down at a curve a little bit, and this piece coming up at a curve. So it kind of looks like a wedge or a piece of pizza. Okay, that's the original piece. We need to draw the mirror image of that over the x-axis. So it's going to look like this. What does that look like to y'all? Pac-Man? Yeah, I can see that. I had some people say a sideways shark fin. I'm like, okay. Now, as a solid, can you see what that's going to look like? Can you see it as a solid? Okay. The bowl has a base, and it's right here. It's on its side. Do you see that? Do you see that it's hollowed out in the center? And it is kind of a bowl shaped, yes, with curved in sides and then a scooped out center.
Yeah.
Okay? So, when we draw our slices, we have to go from piece to piece. So it would go here, all the way from top to bottom. But what is different about these slices compared to the ones that we've done before? They're hollow in the center, and that's very important. I didn't draw this as well as I have in the past. So I'm going to take that slice, and I'm going to pull it out, and I'm going to draw it down here. Now I'm pulling it out. There's a slice. It's hollowed in the center. The center hole will get bigger and smaller depending on where I slice it. Okay? So we're talking about now not a solid disc, but we're talking about a slice that we call a washer. You know why it's called a washer?
Yeah, it's those little
It's like a little metal washer.
They actually call them calculus in the textbook.
Yeah, they call them washers. Because calculus has been around since the 1800s. They've got to call them something that people know about. Metal washers have been around since then. Okay? Now, the thing is, though, the area of a washer has a different formula than a standard disc. What's the formula for the area? How do you find the area of that thing? Big circle minus little circle. So what we're going to do to distinguish between them, we're going to call that capital R and call this little bitty one little r. So the formula would be pi big R squared minus pi little r squared. Do you agree with that? Isn't that how you find the area of that thing? The big circle minus the cutout center. Let's make it even a little bit simpler. Factor the pi out. And this is the way you usually see it in the textbook. Big R squared minus little r squared, with the pi factored out. Because we always pull the pi out of the integral anyway. Now, what is big R? What is little r? Big R goes all the way out as far as you can go. First of all, is it an X or a Y? It is a Y. Okay? But I have two equations that say Y equals. So let's make it a little clearer. Let's call this Y1 and let's call that Y2. Which one is big R? You may not know for sure. If you don't know for sure, go back to your calculator, trace on it. Am I on the outside curve right now? Do you see my little cursor right there? Am I on the outside curve? Yes. Which curve am I on? Look up in the corner. I'm on cosine. So that's Y1. So big R is Y1. And do you see that little r would be Y2? Little r is Y2. So when we write the integral, it's going to be pi parentheses y1 squared minus y2 squared dx, because it's around the x-axis. Okay, limits of integration. 0. Y'all agree we start at 0? Trace the intersection. Well, actually, you can do this without a calculator. I'm going to pretend like we don't have a calculator. I want you to think unit circle. Where on the unit circle, what angle are the cosine and sine the same number? 45 degrees, right? So that's where they would meet, which is pi over what? No. Pi over 4. That's okay. So we're going to pull out the pi. 0 to pi over 4. Y1 is cosine of x squared minus, I messed up a little bit, that's okay, sine of x squared dx. That's the way it's going to have to look in the calculator. Now, what you can do also is pi integral 0 to pi over 4. Since you've already got the equations in there, you could do y1 squared minus y2 squared dx, if you know how to do that. And have I shown you how to do that?
Yes.
You can do it either way. So I'm going to do it that way, because I like that. Math 9. Well, I forgot the pi again. I'll do it at the end. 0, pi over 4. Alpha trace, there's y1 squared minus alpha trace y2 squared. Where's my squared? Dx, boom. 0.5. What a strange answer. I didn't put the pi in there yet. But still, 0.5 exactly for the volume with all those pi's in there? Yeah. That's what's kind of neat about this. This is pi over 2, or times pi 1.571. Any questions?